Hello all and welcome to this presentation where we will be talking about different technologies and framework which comes under Hadoop umbrella from Apache. So this is a basically two-part series. So this is the first part we are going to discuss. So we'll start with the high level objective of this discussion, this presentation, followed by some of the technologies which are part of Apache Hadoop ecosystem. Uh, Part 1 we will be discussing some of them, and rest we will be discussing in second part. So if you have any questions or any point you want to discuss, just in the comment section on this forum of DZone, or wherever you find this presentation, you leave your comments. I'll revert back as soon as possible. Okay, so objective of this discussion is basically to give you guys overview of Hadoop ecosystem. So basically, if you are an architect or a system designer from a non-analytics background, because Hadoop ecosystem is so big and so it covers so many different technologies, it can get a bit confusing if you're new to Apache Hadoop ecosystem. There are different technologies, there are some overlap between these technologies. So idea of this presentation is basically to help non-analytics and non-big data architects to understand what this framework is all about, what are the different technologies it cover, and what are the best use cases of applying those technologies, so that if you are talking to some client or something, at least you have idea what client is talking about, or what are the different technologies which can fit in a given requirement. So idea is not to make you expert in any of these technologies, or not to compare offerings of different stacks or different vendor with Apache Hadoop technologies. It's not the idea. As mentioned, idea is just to give you overview and detailed use case requirement where this particular technology can fit in. We will talk about those only. So now we'll start discussing some of the technologies of Hadoop ecosystem. So first we'll start discussing with Apache Hadoop itself. So Hadoop is a software library framework that allows for distributed processing of large datasets across clusters of computers using simple programming models. Okay, so basically, if you have a large datasets which needs to be processed uh, in a distributed fashion, say you have a cluster of machines and you want individual machine to process some of that chunk of large dataset, Hadoop is that framework. You don't have to do underlying dirty jobs, if we can call it so. Hadoop framework has ready-made functionality to help us deliver those distributed processing of large data sets. Okay, so it is designed basically to scale up from a single server to thousands of machines with a very high degree of fault tolerance built in. Okay, so you don't have to worry if you are using Apache Hadoop. You don't have to worry about failovers and you know uh, reliability and replication. All those things are built into the framework. So you just write your functionality, what you need to do, and map it the Apache Hadoop. It will take care of distribution of jobs and data replication, data availability, all those things. You don't have to worry about it. So it doesn't rely on high-end hardware or load balancers and fault tolerant machines and those kind of things. It's all into software. It's built into the Hadoop framework itself. Okay, so it's all software based, and it works very well. In fact, it is made to work well with simple machines, simple cheap machines, instead of very high-end servers. Mind it, Hadoop is not a database. It's a framework for processing large data sets, but it's not a database. Okay, so what problems Hadoop can solve? Hadoop platform was designed to solve problems where you have lot of data. Okay, we all know how big big data world can get. So Hadoop is meant to solve those kind of problems, and data can be structured as well as unstructured. Structure means you have your relationships and those somewhat we are familiar with the RDBMS kind of structure, and it can be unstructured log files, web server logs, application logs, real-time feeds without any structure, those kind of things. It can be that also. Okay. Sorry. It's for situations where you want to run analytics that are deep and computationally extensive. So if it's as I said in the previous slide, Hadoop is built to run on a large number of machines, simple machines, cheap machines. So if you need to process large data set, you can distribute chunks on multiple machines, and Hadoop can help you in achieving that. So there are lot of work scenarios and use cases where Hadoop is already in use. All social media, online retail companies, organizations, they do banking organizations, they all do Hadoop analytics. So you can find any good study, and almost uh, all the industries are using Hadoop in some of one way or another. So those use cases are available on the net. So a little bit about Hadoop architecture. Hadoop is designed to run on a large number of machines, but they don't share any memory or disk. So they are independent, small desktop, small machines. They don't share any memory, or it's not a SAN based solution or something. They are all independent machines. Okay, so that really means is that you simply buy a whole bunch of commodity servers, put them in a rank, and run the Hadoop software on each one. When you want to load all of your organization data into Hadoop, what it does is divide that data into pieces and spread across different servers. So you have 1 TB of data. What Hadoop will do, it will distribute that into chunks and assign individual chunks to different servers. Of course, it will take care of replications and failover kind of thing automatically. You don't have to worry about it. There is no one place where you can go and talk to the all of your data. So as I said, it's distributed, different chunks are distributed to different servers. So each server is responsible for that particular piece. There is no single place where the whole 1 TB will be available. Hadoop will keep track which piece is lying where. You don't have to worry about it. And because there are multiple copy stores, if one server is down, the data is still available because Hadoop has taken care of replications and failovers and those things. Okay. Architecturally, the reason you are able to deal with lots of data is because Hadoop spreads it out, and the reason you are able to ask complicated computational questions is because you have got all the processes working in parallel. Okay, so as I said, data is distributed in chunks across multiple servers, and each server will be working on processing that particular piece. So in effect, you have hundreds and hundreds of servers working on small pieces of data each. So you don't need a big server or front high-end server to process 1 TB of data. Instead, you have small commodity servers working on small piece of chunks, and in the end the result will be consolidated and you will get your final output. That's the advantage of Hadoop. You don't have to worry about this. So this is the Hadoop architecture. I have captured two versions of Hadoop. Hadoop 1, if you look at this top part of this diagram, Hadoop 1 has basically HDFS, which is nothing but a Hadoop distributed file system. It's a file storage where all your data reside. And then Hadoop 1 had this MapReduce framework, which used to do all kind of cluster resource management, replications, job tracking, job assignation, resource management, all those things, plus actual processing of your data, which is batch data processing. MapReduce is that framework. So people realized that when server when cluster size, Hadoop cluster size went really large, thousand of servers, the MapReduce itself was kind of becoming bottleneck, because it is doing two things: cluster management as well as batch data processing. So what Hadoop people did, basically they divided this whole map responsibility to two tasks. One is the cluster management. They made a separate component out of it, and second thing which they did, they made MapReduce as one of the framework which can handle data processing. In Hadoop 1 only batch processing was there using MapReduce. So but in Hadoop 2 what they did, HDFS remains same. There is a cluster resource management which is called yarn, yet another resource navigator. So this component will handle only cluster management, and then there are different frameworks. For example, batch, they have reduced it, they have made it MapReduce as one of the framework to handle batch processing. Earlier in version 1, MapReduce was doing cluster management as well as batch processing. Plus now you can integrate other frameworks. For say example, you want streaming, you can add Storm and Spark. We will be discussing about Spark and Storm in coming slides. But so point is that now you get advantage of a separate component handling resource management plus different frameworks depending upon your need. You can do batch using MapReduce, you can do online, you can do streaming, etc. using different frameworks. So that is the advantage we get out of Hadoop 2 architecture. Okay, so what is MapReduce? MapReduce is a programming model which is used to process large data sets in a batch processing model. Okay, so we have, as we were taking an example, say we have 1 terabyte of data. So we can write MR programs or MapReduce programs to process that data. What happens is there is a two-way process. One is map, which basically in simple terms it will divide different pieces. So individual map operation will work on individual chunk of piece. Okay, so say example, you want to sort something or you want to filter something out of 1 TB of data. So there will be map jobs. Each map job will be working on each chunk of data lying with the commodity server. So each commodity server will be executing your map job. Okay, once all those servers or all those individual pieces of chunks of data has been processed, you need to combine the output, you need to aggregate the output to come up with the final answer. That is the job of reduce operation. Okay, so map, you divide and you process individual piece of data, and reduce, you combine the output of those map jobs and come up with the final answer to your query. That is the reduce. So this is the high level MapReduce model. It works on master slave architecture, means you have a master which will be assigning tasks to different nodes and combining the outputs, that kind of thing. If you guys want more detail about MapReduce, there is a very good textbook available. You can always go and look at this book. It gives you detailed design patterns and functionality, which is the best way for a given scenario, what are the best options for implementing a MapReduce algorithm. Okay, so there are different ways. For example, where do you want to do the aggregation, where do you want to do the filtering, all those things. So depending upon different requirements, different models can be used, different algorithms can be used. So this book talks about those. Okay, now we'll move to our second component, which is Apache Cassandra, which is not a Hadoop ecosystem per se. It's not part of Hadoop ecosystem, but yeah, because it is generally used as in big data solutions. So we'll talk about this also. Apache Cassandra is a NoSQL database. We all know what that means. NoSQL means it's not a RDBMS. It's a NoSQL. It's a schema-free database, like RDBMS, which needs to have a fixed schema. Cassandra can have flexible schemas. Okay, so Cassandra is built for very fast writes. So if you have a requirement where you need to have very fast writes into the data store, Cassandra is the solution for that. Cassandra is designed to handle big data workloads across multiple nodes with no single point of failure. Again, like Hadoop, failover and reliability that is built into this. So you have a piece of data, it will be replicated across different machines depending upon how much replication level you want. And so if one server is down, second copy can be reused for your processing. Cassandra addressed the problem of failures by applying peer-to-peer distributed system across homogeneous nodes where data is distributed among all nodes in the cluster. As I said, depending upon your replication requirement, you can configure how many copies you want, so that even if 1 or 2 or n number of copies are down, you still have some copies of that piece of data available to you. So what happens in Cassandra write process when you are writing something in Apache Cassandra? So what happens is that each node will capture a commit log. Okay, so whatever you are writing for that node, it will be written to commit log to ensure that is durable. Data is then indexed and written to a in-memory structure. Okay, once data has been committed into commit log, there will be a data structure, in-memory data structure, which is called mem table. Okay, so it will be written and then indexed also in that memory structure. Once that memory structure is complete, full, the data is then flushed onto a disk, which is a SS stable data file. So all writes are automatically partitioned and replicated throughout the cluster, so you don't have to worry about it. How replication is happening, how partitioning is happening, Cassandra will handle that for you. Using a process called compaction, Cassandra periodically consolidates SS tables, discard obsolete data and tombstones. Okay, so it may happen that over time your system is, your Cassandra data store is becoming kind of fragmented. So Cassandra handles that using compaction, where it will consolidate or merge different SS tables, and if something you have deleted, it doesn't delete it initially, it marks it as a deleted called tombstones, so it will clear those tombstones and everything. Cassandra does it automatically for you. That is the process when actually write happens in the Cassandra. Okay, so say you are reading or writing something out of Cassandra. What happens is that your client request can be sent to any node in the cluster. When a client connects to a node with that request, node serve as the coordinator for that particular operation. Okay, so it may happen that your cluster has say 5 nodes. A client is connecting to node 1 for requesting a data which is lying onto node 3 and 4 with 2 replication copies. Okay, so what happens is that the coordinator on which the client connected, it will act as a proxy between the client application and nodes that own the data set being requested. Okay, so coordinator will pass that request to the node where data is actually present, and coordinator determines which node in the ring should get the request based on how the cluster is configured. For example, you have the when you are setting up the Cassandra, you have the options how to configure partitions and those kind of things, how the replication will happen. So depending upon those, coordinator will pass the client request to appropriate node. Okay, so this is how Cassandra actually read write and happens, how high availability works. So if you look at the step 1 on the left side, client writes to any node, any Cassandra node, coordinator node replicates to nodes to all nodes and zones, node returns acknowledge back to the coordinator. Coordinator is basically where client connected, and then coordinator returns the acknowledgement to the client. Data returned through the internal commit log disk. Okay, so once data is written to the internal commit log, acknowledgement will also be returned to the client. Okay, so if a node goes offline, hinted or handoff will complete the write operation when the node comes up. Okay, so what happens that if the data which needs to be written, that node is down, so there is a process called hinted handoff. So hinted handoff means one of the node will carry the hint that this data was supposed to go to the node which is down. So whenever that node comes up, the down node will be given a hint that we have a pending workload for you. Now you are up, you can sync back to the latest data using that piece of data. Okay, so this is how actually it happens. Request can choose a wait for one node, quorum, or all nodes through acknowledgement the write. Depending upon the configurations, how much consistency you require, you can wait for single write or until all the replication has been completed, depending upon your application requirement. So where do you need Cassandra? When you need to scale by partitioning data, when you don't need transaction support. Okay, Cassandra doesn't support transaction supports. If you have a requirement for transactions, go for the RDBMS. Finally, there is a by default Cassandra is eventually consistent, means finally your data will be in consistent state once all the replications, all the hinted sign off etc is processed. If consistency is paramount, go for RDBMS again. But this eventually consistency is also configurable. You can have high level of consistency or even low level of consistency configured in Cassandra. If you need high availability, of course Cassandra is the solution because of failovers, automatic failovers and replications. If you have requirement for geo distribution, multiple location data centers, Cassandra is the solution for that. Cassandra is optimized for writes, fast writes. So if you have a requirement where writes needs to be very fast, Cassandra is again the solution. But Cassandra doesn't have full support for all kind of aggregations and query abilities. So if you have requirements where you need to do aggregations, lot of aggregations and querying based on range queries or joins, Cassandra is not the solution for you. If I compare Cassandra with the say RDBMS, RDBMS deals with structured data, Cassandra deals with unstructured data. RDBMS has a fixed schema, Cassandra has a flexible schema. RDBMS table is an array of arrays, basically row and columns. Cassandra, you have a nested key value pairs. So we have a row, we have a column key, and we have a column value. So it's a nested kind of things, kind of hash table kind of things, nested. Okay. Database is the autonomous container that contains data corresponding to an application. In Cassandra, this is called key space. Key space you can consider something as a schema in RDBMS, not exactly, but something like that. Tables are the entities of the database, and table or column families are the entity of key space. RDBMS supports concept of foreign keys and joins. Relationships are represented using collections in Cassandra. Okay, so if you have a relationship to model, you need some kind of collection where it's a nested key value pair, nested column families. Apache Hive. Now we'll discuss about Apache Hive. Hive is a basically wrapper which gives you SQL like functionality to query your database data stores, HDFS data stores. Okay, so one thing is you use MapReduce using Java or other languages and write your Java programs to process the data. But because people have familiarity with SQL and similar languages, which is very easy as compared to Java, Hive gives you that framework. You write a SQL query, basically Hive query, which is similar to SQL query. Internally, Hive will launch Java programs running those MapReduce jobs for you and process the data for you. So it provides an SQL language called HiveQL and transparently converts queries to MapReduce. So this is the Apache high level architecture. You have underlying Hadoop ecosystem with data in the HDFS and MapReduce, and you can use command line interfaces, you can use web interfaces or JDBC ODBC drivers. It will automatic Hive framework, basically Hive driver will convert that to MapReduce jobs and do the processing. Now we will discuss about Apache Hbase. It's another NoSQL from Apache, like Cassandra. It is also a NoSQL. So it is based on Google's big table and written in Java, and it runs on top of HDFS. HDFS is nothing but file system storage, Hadoop distributed file systems, and it provides big table facilities like big table like facilities for Hadoop. Okay, it is part of a Hadoop ecosystem that provides random real-time read and write access to Hadoop file system. You have a lot of data in Hadoop, okay, HDFS. Now that is just a file storage. If you need random read, write, etc., you need some kind of database to handle those queries. So Hbase is that database for you. If I compare Hbase with HDFS, HDFS is a distributed file system storing suitable for storing large files. Hbase is database built on top of HDFS. HDFS does not support fast individual record lookups because it's just a storage. Hbase provides fast lookup for larger tables. Okay, if you need to pinpoint to a particular record in large collection or fast lookups, Hbase is the solution for you. HDFS provides high latency, okay, because batch processing. It provides low latency access to single row from billion of records, random access. Okay, so HDFS for batch processing. but if you need individual access, random access, HBase is the solution for you. HDFS provides sequential access. HBase internally uses hash tables and provides random access, and it stores the data in index HDFS files for faster lookups. HBase is basically a wrapper around HDFS in a database format, and it gives you all those indexed and all those kind of things to give fast random access. If I compare HBase and RDBMS, again HBase is schemaless. It doesn't have the concept of fixed column schemas, etc. It only have column families. RDBMS is fixed schema. It is built for wide tables and horizontally scalable. RDBMS is for small tables, not thousand and thousand of columns. It's not for that. It's hard to scale as compared to a NoSQL or HBase. There is no concept of transaction in HBase. RDBMS is transactional, we all know. HBase generally will have denormalized data because of the use case it serves. RDBMS will have normalized data. It is good for structured as well as unstructured data or semi-structured data. RDBMS is fixed, it is structured data. And if I compare Apache Hbase and Cassandra, primary objective is random access to data at scale of petabytes. Cassandra is for high availability and reliability at scale. Okay, if you need random access, Hbase is the solution. High availability and reliability, Cassandra is the solution. It is based on Hadoop, HDFS, Zookeeper, name nodes. Zookeeper is basically Apache Zookeeper is a cluster management framework. Okay, so it is basically tightly integrated with Hadoop ecosystem, but Cassandra is not directly related to Hadoop. Hbase supports strong consistency. By default, Cassandra is eventual consistent. Of course, you can configure it for higher or lower consistency, but by default, Cassandra is eventual consistent. It supports range queries and all those things, which is not supported in Cassandra. So this is the high level architecture of Hbase. So in Hbase, basically what happens is you have a table which is split into regions, which you can call kind of partitions, and those regions are managed by different region servers. So one table is split across different regions, and each of those regions will be served by region server, which can have regions from different tables in a region server. Okay, it's a master slave architecture. So what is master? If you look at this diagram, so we have a cluster management tool which is Zookeeper. We have a master server, okay, and we have a region servers, and then Hadoop file system where data stores. So what master server does is it assigns region to the region servers. So you have partitioned the data. Now it assigns each of those partition to some of the servers which are called region servers, and it takes up Apache Zookeeper help in this. It handles load balancing of regions across region servers. Again, maintain the state of the cluster. Is responsible for schema changes and other metadata operations. So this is the job of master server, to handle cluster management, load balancing, distribution of regions and region servers, etc. So regions are nothing but tables that are split across different region servers. Region server has regions that communicate with the client and handle data related operations. Okay, so regions will handle the client request, actually handle read and write request for all the regions under it. So region servers are handling particular regions belonging to different tables, so it will handle those requests and get the data from underlying regions. Decide the size of region by following the region size threshold. Depending upon the configuration you have given, it will determine the appropriate size of that size or partition and do the auto partitioning, auto regioning automatically. So this is the image of a region server. Region server will have a region, okay, different regions, and region will have a store. It stores memory files called memstores and H file, which is actual data store. Okay, so memstore is just like a cache memory. Anything that is entered into the Hbase is stored here initially, and later this is flushed onto the hard disk store file called H file. Okay, so this is the representation of a region server. Okay, so you have different regions belonging to different tables, and you have store, mem stores, which is store which has in memory, as well as actual store files which is an HDFS file system. Okay, so this is the end of part 1, where we covered overview of Hadoop, Hbase, Cassandra and Hive. okay, and the different use cases around those. So if you have any queries, as I mentioned in the beginning, you just leave in the comment section, and I'll revert. Now for further topics, you can go to the second presentation, second part of this presentation, which will be available in the same forum. Thank you very much.